Welcome everyone to the third event of this spring series of talks organized by FunctionalFest. We are a group of Italian developers in love with functional programming. Initially, we wanted to organize a physical conference to gather all the different souls and communities which gravitate around functional programming in Italy and abroad, but that was not possible given the worldwide condition we are at the moment. So we decided to turn to online events, and that's possibly a good thing because we are able to invite great speakers. And so we had some last fall, and you can find the videos on YouTube, and we had already 2 in this series of events. And we will have one next on the 20th of May. We will have Feline Hermans, who will speak about the cognitive aspects of programming. So be sure to follow us and to keep in touch with us. You can find us on Twitter. We are FunctionalFest. You can subscribe to our YouTube channel you're watching right now. And you can check out all we do on our website, which is www.functionalfest.it. And I'd like to thank Doubleloop, which is our technical and infrastructural sponsor. And coming to tonight, we are very pleased to have Nicolas Rinaudo, CTO of Bezeto, as a speaker. He is a Scala programmer, and after he discovered functional programming through it, he made his mission to learn and explain the scary bits by focusing on practical applications. So before giving the word to Nicola, I will ask you to post your question on the YouTube chat if you have any, and we will ask them to Nicola. So Nicola, you're up. Thank you for being here, and the stage is yours.
Thank you for having me. So let me first share the slides. And in theory now, you should be seeing my slides. Is everything working properly?
Yes.
Perfect. So let's get started. Good evening. I'm Nicolas Rinaudo, and I work for a Swedish company called Bezeto, where we do a lot of online content moderation and machine learning. And I'm here tonight because I would like to talk to you about testing, because we're all a little bit weird about testing, aren't we? Let me tell you a little story, and you can tell me later if it rings any bell. A while ago, I got into the office, had to pick up a task for my day, and it was one of these tasks, these things that we have to do every once in a while as engineers. It's a new feature for a customer. Not very fun, not particularly hard, not very exciting at all, just busy work that we sometimes have to do. But went ahead and did it. I wrote the code, followed all the company's best practices, made sure that all the static analysis passed, linter, everything. When everything looked like it was working properly, loaded it up in a REPL, played with it, made sure it behaved as expected. And then I probably should write tests, shouldn't I? But we all know I probably didn't. Didn't really need to. It's a very simple change. It's a couple of lines commit. The types line up. Everything looks right. The static analysis passes. I've even played with it. It looks like it's working. It's a very simple change. None of these arguments are actually any good, but they're not the real reason I didn't write the test, though, are they? I didn't write the test because I didn't want to. It's unpleasant. And the reason I find them unpleasant to write is however hard I try to write the test, however clever my tests are, however many edge cases I find, that very commit I just wrote, that very simple change is at some point, maybe not today, maybe not tomorrow, but at some point it's going to cause some sort of outage. And I hate to play a game where I know I'm going to lose. If, however hard I work, there's still going to be some defects in production, why even bother looking? And of course, there's also the slightly less sane argument that I make in my head. It works in my head. It usually doesn't when I say it out loud, but I can't really be blamed for not finding any bugs if I haven't looked for them, can I? So, and if none of this sounded any familiar to you, if it didn't ring any bell, you don't recognize yourself at all in that story, then I have 2 hypotheses. The first one is, you're not being entirely honest with yourself. And the second one is, maybe if you truly never felt that what I just described, then possibly this talk is not exactly for you, because the promise of this talk is, by the end of it, you will have learned techniques to make testing less painful, less discouraging, a lot more fun, that will find more flaws in your systems, and importantly, that don't really require any more work than what you're already putting into it. But before we can get to that, I need to start at the beginning and define software testing. Software testing, if you reduce it to its simplest expression, goes something like that. You have to generate some sort of test case. Can be very easy, can be very complicated, depending on the situation. And it is known as a test case generation problem. It's one of the problems that we regularly have to fix. And once you have a test case, you need to run it through your system, which is going to yield some output, which you must then analyze and decide whether it denotes an underlying defect in your system. This is known as the oracle problem. And the oracle problem and the test case generation problem are both fairly complicated problems to solve. One that is really easy, however, is evaluation. But before we can get to evaluation, which means before we can evaluate our test cases in some system, we need a system to test. And for the purpose of this presentation, I'm going to use a system that you might already be familiar with. It's a problem that recruitment companies really enjoy giving to candidates. And I think it's a really terrible recruitment test. But it is, on the other hand, a very good way of showing how even very simple systems can lead to very subtle defects that might be hard to find if you don't know how to test things properly. That system is FizzBuzz. And the concept is, given a number, you have to print it. But if that number is a multiple of 3, then you have to print fizz. And if it's a multiple of 5, then you have to print buzz. And that's it. That's all the problem. And we have our implementation right here. But before we show it to the recruiter that's testing us, we need to test it. And the way that most of us at least, have been trained to test things, the way that we do in the industry most of the time, is known as example-based testing, which you probably know as unit-based testing, but that is, of course, not the right name for it. Because unit describes a scope, and example-based testing is a mechanism, is a way of testing things, not a scope. And example-based testing goes something like that. The test case is a known input. You take some input that you already know, process it for you, evaluate it for your system, and then look at the output. And then the oracle problem is really very easy, because since you know the input, then you also know the output. So making sure that your evaluation doesn't denote an underlying defect is just making sure that you get the output that you were expecting. And it's usually very simple, a bit wordy, but very simple. Given a list, for example, if you sort it, then you should get the expected list sorted. And for FizzBuzz, we could write something like that. We'd have these 3 tests, which all look the same, all follow the same principle, given a known input, evaluate it in FizzBuzz, and make sure it's equal to the expected output. The tests we wrote are, first, make sure that FizzBuzz of 3 is equal to fizz, FizzBuzz of 5 is equal to buzz, and FizzBuzz of 7, which is neither a multiple of 3 or of 5, is equal to 7 as a string. Armed with that test case, that test suite, we execute it, and we realize that there is no defect. So we proudly send that to the recruiter, who promptly passes 15 as an input. And that, of course, doesn't behave as we'd expect, because 15 is a multiple of 5, that doesn't yield buzz. And this is exactly why I think FizzBuzz is such a bad test for recruitment, because the reason that we failed here is because the specifications were written specifically in a way to trick you. The person who wrote the specification knows that there might be a problem here. They could outline it. They could say, this is a trick, make sure you do that when that happens, but they have decided not to. And if the company that wants to recruit you considers that working out tricks that have been left in the specification specifically to trap you is a good skill to have to work for them, maybe you should consider not working for them instead. Right. So if your recruiter or the person who wrote the specification was any good, he'd have given you something like, sorry, yes, you failed the job interview. You would have gotten something like a decision table. It's very simple thing that most people have studied but forgotten about. It goes something like this. You have a column that describes the shape of your input. Here, for example, now we have a column describing whether n is a multiple of 3. The second one is whether n is a multiple of 5. And finally, the last column tells you the expected output. And if you look at it, you can see clear as day on the first line, if n is a multiple of 3 and a multiple of 5, then the output should be fizzbuzz, which fixes another ambiguity, doesn't it? Because technically BuzzFizz would have worked as well, but the recruiter expected fizzbuzz. So now that we know exactly what we need to test, we can fix our fizzbuzz implementation. We can, in the case of your input being a multiple of 3, we can fix that to check whether, if it's also a multiple of 5, then you return fizzbuzz. If it's just a multiple of 3, then you return fizz, and you leave the rest of them. Of course, we need to amend the test cases to the test to test whatever it is we just wrote. It's very straightforward. Given 15, we expect, after evaluating in fizzbuzz, to get the string fizzbuzz. And if we evaluate this test suit, we do not find a problem. This looks like it's working. So we pass that to the recruiter, who tests a negative number. And this promptly failed again, because fizzbuzz means that the input was a multiple of 5, and clearly -3 is not a multiple of 5. And here, the problem, the thing that tricked and failed us, is not the specification. It's us, it's ourselves. We tested everything we thought of implementing. We brought our bias from the implementation to the tests. So we haven't tested anything we haven't thought of. By definition, if we had thought about testing it, then we would have tested it. And that's not sufficient. The thing we've learned so far is example-based testing is really very good at the Oracle problem, because it's very easy, given an output, to decide whether it's the right one, because you know the output you should be expecting. So it's trivial. It's not very good, however, at the test case generation problem, because you have to do all the work yourself. You have to come up with every single test case. You have to think of all the edge cases you want to test. You have to be as exhaustive as possible. And you can't be really expected to. I mean, you're a human person. You can't be 100% of the time at your best. And this is what example-based testing requires of you. You need to be perfect to write good test cases, which is very discouraging, because you won't be perfect all the time. You will fail, you will cause defects, even though you have worked really hard at the test cases. And if we want it to be exhaustive, even very simple system can get prohibitively expensive. Take fizzbuzz, for example. It only takes an int as an input. That's more than 4 billion possible values. And we have tested 4. Not exactly a good ratio. So this is not good enough. We need to do something better. And one way of solving this problem would be to use what's known as generative testing. The concept of generative testing goes something like this. Instead of taking a known input, take a random one. Then you evaluate that random input and look at the output. But then this becomes a little bit more complicated, because you know nothing about the output. Since you don't know anything about the input, then you don't really know anything about the output either. So how do you decide whether the output you got denotes an underlying defect in your system? One solution, it's not the only one, but one solution is to use what's known as properties of your system, hence the name property-based testing, which is a property that you know all of the outputs of your system will have, and then you make sure that's respected. For example, sorting a list. We know that for any list of it, if you sort it and you compute the diff of that with the original list, then the diff should be empty, because when you sort a list, you will get exactly the same elements. Maybe not in the same order, hopefully, but exactly the same ones. They will not delete any integer or remove any or create new ones. For fizzbuzz, we could write the following property. For any int, if it's a multiple of 3 and of 5, then we expect fizzbuzz. If it's just a multiple of 3, we expect fizz. Just a multiple of 5, we expect buzz. Otherwise, the input has a string. And this property, of course, will not find any flaw in the system. Because if you look at the property we wrote, that's basically the fizzbuzz implementation that we wrote. We we've fallen into a very common trap. We have re-implemented the system under test, which is both the worst property you can write and the most common mistake in the field. We don't want to rewrite exactly the same system that we wrote, because then we fall right back in the trap of example-based testing. We bring our own bias with us. Instead, you have to come up with properties that are not re-implementing the system. And this sounds a bit vague, because properties are very diverse and can be very hard to find. It's usually one of the issues when people try to learn property-based testing is, how do I work out, how do I come up with a good property for my system? And luckily, there's a trick. There's a known set of properties that apply to most systems. It's not that all these properties apply to all systems, but most systems will have at least one of these properties. And if what you do is you take this set of properties in your system and check whether each property applies to your system, then by the end of it, you will have a couple of good properties to start from. So let's do that for FizzBuzz. The first property that we could have is an oracle, which is a brilliant situation to be in. Because sometimes you have a reference implementation. And if you have a reference implementation, then you can evaluate your random input in your system and in your reference implementation, and then the two are linked by a property because they must be equal. For example, list sorting. I have implemented my own very fast list sorting algorithm. It works in O of 1. And a property that it must have is that for any list of it, then sorting that list with my system and with a reference implementation in the standard library should yield the same output. Otherwise, you found a flaw. And this is an extremely useful property that you will have every time you refactor, you rewrite, you optimize part of your platform. Say, for example, that you're working for an online music streaming company, and you have an API that allows you to search for specific tracks, so a find tracks method somewhere. And somebody very clever in your team came up with a way of making it much, much, much faster. Well, then you have a property right there. What you do is you take your find tracks implementation and copy it in your tests. And then for a given query, evaluating it in both of the find tracks method is going to yield results that must be equal. And that is your property. Because if they're not equal, then you have found a flaw in the system. Unfortunately, FizzBuzz doesn't have an oracle that I know of. So this property doesn't apply to FizzBuzz, but others might. So let's keep going through the list. Another very simple property to have, and most systems have this one, is validity. Sometimes it's possible to know whether the output of your system is not necessarily the right one, not correct, but valid. It's a possible output value for your system. And in that case, your property is just checking for validity. For a concrete example, absolute value. For any int, the absolute value of that int must be non-negative. And this is it sounds a little bit weak as a property. It doesn't sound all that useful, but if you think a little bit outside of the box, a lot of systems have such a property, which can be extremely useful. Take, for example, our search engine that we're talking about. If you run a given query string through the search engine, you run it through the search engine, and you get the list of results. And if any of the results doesn't match the query string, then you found a flaw in your system. FizzBuzz has such a property. For any int, we know that evaluating that int in FizzBuzz must yield a value that is either FizzBuzz, or the input as a string. Probably not going to find any bug this way right now because we've seen the implementation and we only yield values that are valid. But the interesting bit about what we've just done is that now we know for a fact that FizzBuzz will always yield correct values because this property will prevent illegal implementation from passing. All right, so this is a new property for FizzBuzz. Let's look at the rest. Involutivity, which is a kind of a complicated name to mean that your system has an inverse. And if the system has an inverse, then instead of evaluating instead of checking a property of your evaluation, you will check a property of the inverse of your evaluation. This must be linked to the original input because both of these things must be equal. As an example, for any int, getting a textual representation of that int, then passing the resulting string as an int must yield the original input. This is an extremely convenient property to have. For example, whenever you have to do serialization and deserialization, encoding and decoding. Typical example, one that I actually run a lot in my office. Very often when you have APIs, you are going to send your data types or read them off of the internet, more often than not as JSON. So you have one of the data types, it's a track. And you have some sort of encoding function that turns your track into a JSON object. And then you have a decoding function that goes back from the JSON object to the track. And if there's a difference here, then you find a flaw in your system. And this round trip property, when you have it, is a godsend because you can get extremely good tests very, very cheaply. It's just generating a value and then decode of encode of that value should be equal to that value. Done. You have a property that's most likely going to find the vast majorities of the bug in the system. FizzBuzz is kind of involutive for any int that is neither a multiple of 3 or a 5. Because if it is, then you're going to get fizz, buzz, or fizz buzz, and you can't get back from that. That's you've lost the original input. But if your int is not a multiple of 3 and a 5, then evaluating it in FizzBuzz and then passing the result as an int should yield the original input. This property doesn't yet found the bug that we're looking for, but it's still another property that we have added to our bag of tricks. Then we have idempotence. Now this word, it's one of these words that however often I look up how to pronounce it, I looked it up right before I started giving this talk, just to make sure it was still fresh in my head when I got to this point. I forget it within 10 seconds. So if the first time you encounter the word idempotence, don't base your pronunciation of it off of mine because it's likely incorrect. I'm just doing it with a French accent. It's probably not the right way to pronounce it. But idempotence means that whether you evaluate a system once or many times is going to yield the same result. So then the property is evaluating it once or twice should yield the same result. For example, list sorting. For any list event, sorting it once or twice should hopefully yield the same result. And idempotence is a property that a lot of systems have, even though you don't necessarily realize it. Most of us have or will work on CRUD systems, create, read, update, and delete systems. As long as you're working with database, you have plenty of idempotence to go around. Take this, for example, database of tracks. If you run a query to delete one of these tracks, then it should be deleted. But if you run it a second time and the database changes, then you find a flaw. And it applies to creating a value. If you create a value twice, it should only happen. It should only appear once, shouldn't it? If you update a field of one of your value to a given value, then that should only happen once. FizzBuzz, unfortunately, doesn't have this property. Then we have the invariance property. Some systems have an own invariant. Usually systems that have been studied mathematically, you know something about that function that is always true. And in that case, your property is just checking for that invariant. Typically, the one example I gave you earlier, for any list of events, sorting it and computing the diff with the original list should yield the empty set. Now, invariance sounds like it only applies to systems that have been well studied. It sounds like a very mathematical concept, something that's not useful to your day-to-day work, but that's because everybody keeps forgetting. One invariant that most systems have, hopefully, is that they should not crash, they should not throw an exception, they should not core dump, they should eventually at some point return. And just that property can be extraordinarily useful. Let me tell you a little story. John Hughes, the person who invented property-based testing, was once working on a database system. And the problem with the database he was working on is that every once in a while, for no apparent reason, it gets corrupt. And I got so tired of that because it is a bit of a problem. And you have backups that you can reload, but still it's a bit of a problem, a database that gets corrupt every once in a while. They got so tired of that they decided to spend a few man weeks on trying to solve the issue. So people looked over the code for weeks and trying to find what caused the issue and couldn't find anything. Complete blank, no idea what was the cause of the problem. Up until the point where John Hughes got a little bit tired of the whole thing and decided, well, it is a property of a database that it should never crash, isn't it? That it should never get corrupt. So what I'm going to do is I'm going to generate random lists of commands, execute every single one of these commands, and after each one, the database should not be corrupt. And if it is, you have found a flaw. And just like that, in a couple of days worth of work, he found the problem that they'd been looking for weeks. In fact, I say the problem, but he found, I think, if memory serves, 3 distinct problems that would cause database corruption. The one that they were looking for, plus 2 completely new ones that they had never heard of. People had looked for that bug for weeks, but using this very simple property, my system should not crash, found 3 distinct bugs that people could not find at all. So any system should have at least this property. It should not crash. In the case of FizzBuzz, we do have that. Of course, we have that property. For any int, evaluating it in FizzBuzz should not throw an exception. Of course, we've played with that implementation for quite a while now, so we know that we're not going to get a crash. So we get to our last property, metamorphic relation, which is a very complicated name, but it's actually fairly simple. Sometimes, if you have your random input and you transform it in some way, and then you evaluate that as well as your original random input, then there's a property that link the 2 evaluation, which is known as a metamorphic relation. To give you a concrete example, take a function that computes whether a number is a multiple of 3 or not. For any int, check whether that int is a multiple of 3. Then take its inverse and check whether that is a multiple of 3. And the 2 should be equal, because if a number is a multiple of 3, then its inverse must also be a multiple of 3. And metamorphic relations are kind of odd. You kind of have to put some thought into it because you have to think in a certain way. But when you do, you're going to find some really weird bugs and some really good properties. An example of that is our previous search query in a database. We have run a search, a query, and got some results. Now take the same query and add a new criteria. Now run that query, and it should, since it's more restrictive, you should probably get fewer results, or maybe, if you're not lucky, exactly the same results, but certainly not more results, because then you found a flaw in your system. And people might say, well, this looks unlikely. How could such a bug exist? I mean, this is not going to work. Well, it does. It really does, because there was a study made of that, of the Spotify and the YouTube public APIs. And they found 3 new unique bugs in the Spotify API and 8 new ones in the YouTube API. So it does find flaws. Also, I mean, if you've been following, we are up to the last properties that we're going to study. And we haven't found the bug in FizzBuzz yet. So clearly, this is how we're going to find our bug. And there is a metamorphic property, a metamorphic relation for FizzBuzz. For any int, if I evaluate FizzBuzz on that int, and take the inverse of that int and evaluate it in FizzBuzz, then if the first one contains fizz, so should the second one. Which makes sense. It's exactly the same property that I showed you earlier about checking whether a number is a multiple of 3, isn't it? It's just now we're putting FizzBuzz in the middle, but still very good property. And when you run it, you immediately find the problem. If you pass -1, you get a bug. Now that we have a test that we can use to make sure to reproduce consistently the bug that we have, let's look at the code of FizzBuzz. That bit here, that looks a bit dodgy, doesn't it? Somebody, well, me in this instance, try to be a little bit fancy, a little bit too cocksure, try to show off a little bit to everybody. But that's not really how you compute whether a number is a multiple of another, is it? Thing is, we haven't tested these functions because we didn't write tests for it. However simple the system, we still managed to find ways to fail it. But luckily, we did come up, while we explored properties, an interesting properties here, which is prop not 3. If a number is a multiple of 3, then its inverse must also be a multiple of 3. And that finds the bug immediately. So we know now that the bug is in how we check whether a number is a multiple of another. Let's rewrite that. Let's rewrite it in such a way that it doesn't look so dodgy. Let's use the regular implementation, the one that most people should be familiar with. And once we've done that, and we rerun the properties that we had, then we immediately notice that we fixed the problem. And then if we retest our FizzBuzz property, or metamorphic relation for FizzBuzz, then we now have a working FizzBuzz implementation. Now, typically, when you get to that point, you run through all the known properties, and you found a few that matched your system. What you do is you aggregate them together. This is all of our properties, the validity one, the involutivity one, the metamorphic relation, and the invariant. And you make sure that everything still passes. It does. And now this is where the game begins. This is where you have a working set of properties that you're happy with, and you try to come up with a flawed implementation of FizzBuzz that is going to fool these properties into accepting it. A very good way of doing that is pair programming. You get somebody else to write the bad implementation. You do the properties, and they find ways of fooling you. Here, for example, nowhere in our properties do we check that a multiple of 3 yields fizz and a multiple of 5 yields buzz. So let's say we swap this and see what happens. And if you run your properties, they will pass, which initially you're very happy about because it means, yes, my properties are good. But no, they're bad because we pushed a flawed system and they still accepted it. So we still have a problem, and here it's very easy to fix. Here's a property. It's an interesting one because it doesn't match any of the properties we described before. For any int, if you multiply it by 3 and evaluate FizzBuzz on it, then it should contain fizz, because any int multiplied by 3 is a multiple of 3 by definition. So this is not one of the properties that we have defined before. It doesn't fall in any of the categories that I told you about, because these categories do not define all possible categories, just the ones that are very common. And then you're going to find some other properties that work for your system only. And now that we have a digital property, if we run them, we immediately find the problem. What we've learned here about property-based testing is property-based testing is really very good at the test case generation problem, because random input, right? So you're eventually going to cover the entirety of the domain of the test space. So you can't really get much better than that at the test case generation problem. It's also pretty good at the Oracle problem as well. But I need to address the elephant in the room now. Hopefully this has so far been an interesting talk. You've learned a few things, good delivery, good argument. But I told you, I promised you in the beginning, this is going to work without much more work than you have put in your current test so far. And it sounds like a lot of work, doesn't it? You have new skills to learn. You have completely different kind of tests to write. And you're not going to go back to your office tomorrow and look at your page and pages of example-based testing, example-based test, and convince your CTO, well, let's rewrite all that. We hate writing tests, but let's throw away everything that we have already written and rewrite everything using property-based testing. That's never going to happen. And all of these things are true, but that's just because I haven't showed you how to cheat yet. Because we can do something that's called generative example-based tests. This is not an actual word. I made it up for this presentation, so don't look it up on the internet. Not going to find much of it yet. But the concept is this. If you take your example-based test that we wrote at the beginning of the presentation, look at them. Look at this one. Specifically, that bit. Well, that looks a little bit like a property, doesn't it? This says, for any int that happens to be free, then the output of FizzBuzz should be fizz. So let's turn that into a property. And this tree here, well, it doesn't look very good because when we write properties, we try to express them as for any of something. So let's do that. Now, what we've written here is that for any int that happens to be the constant free, then if we evaluate that int in FizzBuzz, we should get fizz. Now, this is a good property, but it tests one input. And seems a bit of a shame because really the point of this test initially was not to test 3, but to test numbers that are multiple of 3, but not multiple of 5. So if instead of generating the constant 3, we could generate numbers that are multiple of 3 but not of 5, then we would have a very good property. And this is fortunately very easy to write. For any int, multiply it by 3 and remove anything that's a multiple of 5. And armed with this new generator, we can replace a constant by our generator of multiple of 3s, and we have a very good property. We could take it further though, because if you look at it, the moving bits are what kind of input am I testing? And for that kind of input, what kind of output am I expecting? If this reminds you of the decision table I showed you earlier on, that's not at all a coincidence, of course. So we can turn them into parameters, so we are capable of writing every single line in our decision table. So prop_FizzBuzz becomes a function that takes a generator of ints, and of course, we must use that, and an expected output, which we must update. And this new prop_FizzBuzz is a generic function that will allow us to create all the properties we need for FizzBuzz. For example, prop_FizzBuzz3 is simply a specialized version of prop_FizzBuzz with the generator we just wrote and an expected output of fizz. Now, let's look at the second test case. This says that given any numbers that is a multiple of 5 and not of 3, then we should get buzz. Fair enough, let's write a generator for that. We know how to do that. For any int, multiply it by 5 and filter out anything that's a multiple of 3, and you get your generator. And armed with a generator, we can just make a specialized version of prop_FizzBuzz with the generator we just wrote and an expected value of buzz, and that's your property. This property looks a little bit more tricky though, because, well, given a number 7, which is meant to be a number that is not a multiple of 3 or of 5, then we get the string 7, and this looks a bit harder because this is not an expected output, is it? It's based on the input, it's not hard-coded. So we might have a bit of a problem here, but let's soldier on and see how far we can get. The first thing we need to do is to write a generator for numbers that are neither multiple of 3 nor of 5. Fairly easily done. Take any number and filter out anything that's a multiple of 5 and a multiple of 3. And then when we try to write our property as a specialization of prop_FizzBuzz, using the generator we just wrote, we get kind of stuck here because we can't put a hard-coded string here. This depends on the input. That's easily solved though, isn't it? Instead of taking an expected output, we put in an oracle, a function that, given an input for that specific kind of test, knows the output. So for any int generated by the generator that we've passed, this is the correct answer. And now with that, we can write our property such that the oracle is whatever the input was, but as a string. And that only works for multiple numbers that are not multiple of 3 nor of 5. And that gives us a very good property. And once we've had that property, finally the last one, which says that for any number that is a multiple of 3 and of 5, if we write it in FizzBuzz, we should get the string FizzBuzz. And well, we need to write a generator for numbers that are multiple of 3 and of 5, which is easily done. Take any number and multiply it by 3 and by 5. And that give us the final properties that we were looking for with the generator we just wrote and a function, an oracle, that discards the input and returns FizzBuzz. And what we've learned here is you don't need to learn a new way to write tests, not right away at least. You can use all of the skills you have developed over the years, all of the intuition you've built up on how to find edge cases, everything you've done so far, it still works. You can adapt existing tests with very little work You can take the test you wrote, but instead of taking a hard-coded input, generate a random input that matches the problem that you're trying to test. And as you do that, you will acquire the skills you need to learn, to have, in order to start writing some of the fancier properties. But really, you might not ever even need to. If you can write properties like I just did, based on example-based test, you already have improved the way you write tests by quite a lot. Now, in closing, if you only remember just the one slide, it's the one to remember because it's an important one. It's the one where I point out that I delivered on my promise. I told you that you would find more flaws than you used to, and property-based testing will, simply because it doesn't rely on you to find the bad test cases. It doesn't rely on your intuition and your knowledge, on the bias that you already have. It's going to explore the entire testing space to find problems. It doesn't need to be harder than example-based testing, because it can be basically example-based testing up until the point where we want to take it to the next level. But you might never have to. And finally, it can be quite a lot of fun, because doing this game where somebody writes a property and somebody else tries to fool the property can be a lot of fun. And before I close here, I want to leave you with an interesting thought. It's something that I've always meant to play with and to try out. I never found the time, but properties have an interesting characteristic. Properties don't need to know anything about the input in order to know whether the output denotes an underlying flow in your system, do they? So you could evaluate them on random input. That works, it's okay. But you could also evaluate them on much, much more interesting input, couldn't you? You could evaluate them on live input, on input that your platform actually sees. Because these are by definition interesting inputs because they are data, there are test cases that actually happen in real life. And you probably, when I'm saying that, you're probably hearing, right, okay, log the traffic, the platform's live traffic somewhere, then pass that and run this in the tests. And yes, that's clever, but everybody's been doing that for ages. And that is completely true, but it's not what I mean. What I mean is evaluate the properties in production. This would give you what I think is a very cool metric, because we already have plenty of metrics to test whether your system is healthy. We have CPU usage, memory usage, all these things. They tell you whether the platform is healthy. But if you have another metric that tells you number of properties validated divided by numbers of properties evaluated, then that tells you how sane your platform is. And I think it would be a very cool metric to have. Now, having said that, do you have any questions? Because if you don't, and I still have time, we can talk about metamorphic testing, which is also very cool.
Okay, Nicola, I was following the chat on YouTube, and until now there's no question from the audience. So I think that if you have some bonus material, you can go on while we wait for questions arising for the audience.
I absolutely do have some bonus material. So just interrupt me when I'm running out of time. Right. Okay. So one of the things that comes up every once in a while when you're doing property-based testing is sometimes test case generation is extremely expensive. And you can't reasonably be expected to generate it randomly because it's prohibitively expensive. There's a solution for that, which is the one I want to bring up now, which is metamorphic testing. Again, a name that we've seen not too long ago that sounds very scary, but it's very simple. But in order to introduce that properly, I need to tell you a story. See, as I said in the introduction of this talk, I work for a company that does machine learning and online content moderation. And one of the things we do is for online dating sites, make sure that the profile that people create for themselves are up to specifications. And one of these specifications is the profile picture of them, or maybe not of them, but of someone and just one person. We need to have only one person in these pictures. And the solution we found to that problem is to use a machine learning model that, given a picture, would put a bounding box around the faces that it finds in the picture. And if we find exactly one bounding box, then this looks all right. But if we find 0 or more than 1, then some action needs to be taken. We could reject the profile or ask for a human to moderate it, for example. But such a system is really very hard to test, isn't it? Because the only way to test it that I can think of, initially at least, is to have one picture with a known bounding box and making sure that when we evaluate it in the model, then we get the right bounding box roughly. But that means that for every picture that we want to use as a test case, somebody must outline it by hand. That's a lot of work. Now, it's not impossible to do. I mean, interns are a thing, so there's a technical solution to that problem. But when you do online content moderation, faces are one of the least offensive things that you have to look for in pictures. And I couldn't ask anyone to spend hours or days or weeks outlining other miscellaneous body parts. So we had to find a better solution. And somebody came up with this notion that if you know the image and you know the bounding box, then you could transform that image. If you flip it, then the bounding box is going to move around, but you know exactly where it's going to end up. You just apply the same transformation. Then if you rotate it, same thing. Finally, if you change the color scheme, you can still predict where the bounding box is going to end up, can't you? So we just went from, this is going to be really very hard, every single example is going to take a lot of work, to, given one example, I can generate an infinite number of other test cases. But while this is very good, a lot better than what we previously had, it's still not great, because it's still going to be variations on the same symptoms. It's still going to be a picture of me when I was younger. But then somebody else pointed out, well, hang on a minute, we do have a system that knows how to predict what the face is going to be. It's the system that we're testing. So what if, instead of manually annotating it, we took the original image, ran it through the system, but transformed it in a random way, computing where the bounding box should appear, run that through the system, and then compare the two that make sure that the bounding box match. Because if they don't, then you find a flaw in the system. Now, it's not a perfect property, because you can find some trivial examples of systems that will be flawed but pass this test. Typically, the system that predicts no face is always going to pass it, which is why it's not enough. You still need a few example-based tests to complete the bag of tricks. But this is a very good property to make sure that your system is sane. And that is what metamorphic testing is. Given a test case, transform it, evaluate both, and make sure that they fulfill a metamorphic relation. In our previous case, that the bounding box should match. And this diagram should feel very familiar, because it's exactly the one that I had for the property of metamorphic relation. Except here, we realize that we're not working on a random input or a known input. It works on any kind of test cases. A concrete and very fun example of metamorphic testing that was actually very useful is the following. When you're looking for bugs in a compiler, it can be really very hard. But a very good trick is take some known program, FizzBuzz. We've been talking about that for a while now. Evaluate it on known input and store that input somewhere. Keep it in mind. Look at the output and store that output somewhere. But also run code coverage tools on your code so that you know exactly which code was involved in producing that output. But a lot more importantly, which code wasn't involved, which code is dead. Because that code was apparently not involved at all in coming up with the output. So we could remove most of it, even mutate it somehow. And this should not change anything, because, as I said, this code was not evaluated before. It wasn't run, it wasn't executed. So changing it should change nothing. But if you run again your system on the same input and you get the same output, then you're fine. But if you get, say, ZIF, for example, then you find a flaw in your system. And, well, this principle was actually trialed. People made a study of that and found 79 new unique bugs in JCC and 68 new unique bugs in LLVM. Those are not pieces of software that people don't use much. They're used all the time, constantly on more and more complicated inputs, and yet people hadn't found these bugs. So that's quite a good property to have and very simple to put together. As a side note, since the study was published, the people who ran the study also tried it on next version of the Scala compiler. And they only found 42 new unique Scala C bugs, which I think is conclusive that Scala is clearly a better language than these other two. Now, what we've learned about metamorphic testing here, that it helps generating test cases when it's too expensive. So it helps with the test case generation problem. For my images, for example, it was really very hard to find to create test cases for our machine learning model. But metamorphic testing allowed us to have an infinite amount of test cases for very, very cheap. It also helps with the Oracle problem, because sometimes it's really very hard to decide whether or not an output denotes an underlying flow. But again, metamorphic testing here allowed us to find images that didn't match or underlying bugs in compilers in ways that were non-obvious. And it's also a very good word to use when you want to sound smart in a public company. And now, do we have any questions?
Okay, good. In the meantime, we had some questions from the audience. So let me read them for you. So property-based testing seems pretty awesome, but the pain points are when we have to write the shrinker and printer. So do you have any insights about it?
I know who asked that question. Okay, yes, absolutely I do. It's completely out of scope for this talk. Yes, absolutely. I didn't want to talk about shrinking and printing. There are techniques to completely and entirely automate that. I can point you to a very cool Haskell paper called Shrinking and Printing Functions that does exactly that. Now, the person who asked that question is a troll, but to the other people, one of the critical aspects of property-based testing that I didn't get into at all is that if you do it right, not only is it going to generate test cases that fail your system, but it's going to generate minimal ones, which is why for FizzBuzz, we got -1 and not minus of 700,000. This process is called shrinking. I'm not going to get into how it works because this is something I'm actually working on at the moment, so I don't want to spoil it. But shrinking is a concept of taking one value and making it smaller and smaller and smaller until you find the smallest possible value that finds that still fails the system. And so what the person wanted me to say is that you can generate random functions with probability-based testing. It's actually very simple. But it's very hard to shrink a function, and it's very hard to print a function. And how would you solve that problem? That's an hour and a half worth of talk. I don't think we have the time for that. So here's my answer. Do we have any actual question now?
Okay, so let's try with the second one.
No, the thing is, it's a friend of mine who follows me on every single one of my talks and always finds the most unpleasant question to ask at the end to make sure that I lose my cool and kind of get derailed. So it didn't work this time.
So another question is, isn't there a risk that by modeling our properties, we are effectively duplicating the logic we are trying to test?
Right, so when I introduced property-based testing, that was my very first point. This is the very first thing that everybody's going to do and exactly what you should not be doing. It's the worst property you can possibly write. So there is a risk, of course. And you must be on the lookout for that risk, because even if you know what you're doing, even if you know that re-implementing a system and a test is a problem that you might fall into, you might still fall into it in very roundabout fashions. But the techniques I gave you, the first ones are going through all the known set of properties, metamorphic, involutivity, and all these things. Well, none of this involve rewriting the system on the test, because you don't actually check against expected output, do you? And that's a problem with probability-based testing that most people struggle with. You want to rewrite the system because you have been trained to do example-based testing. You have been trained that a test is only useful if you can actually look at the output and make sure it matches what you expected. And the only way to do that is to either know the output or re-implement your system. But these don't work like that, and you have to train yourself out of it. This is where the second part of what I try to explain comes in, where you can write your example-based testing, you can view your inputs and your outputs. You can do exactly that, but then generalize them, make them into properties. Those are weird properties because they're only defined on part of the system, each and every single one of them. They're just another view, another way of writing a decision table. But when you do that, you cannot duplicate the logic of your system because you are only working with much, much simpler systems. Every single time, every single line of the decision table that you write is a much smaller system that just works for a given category of inputs. So for example, if n is a multiple of 3n of 5, then the system that you re-implement is just fizzbuzz. You don't have to implement the logic, just the expected output, and that still works. So it is a risk, but once you're aware of it, then you pay attention to the things that I try to teach here, then you should be able to avoid that problem.
Okay, so now a question about the input, the generated input. I'll try to rephrase the question actually. So how can you be sure that you are creating reliable generators? So for instance, the question mentions if you have a base 64 encoding function, which should be, when decoded, should be an actual valid sentence in French or Indian, Korean, or whatever language you want.
Oh, so let me try and rephrase that question to make sure I understand it properly. The question is, generating random value is very easy when you have to generate an int, but some test cases are much more complicated. And how do you generate such complicated random values? It's both a good and a bad question. It's a good question because it's actually a problem. It's a bad question because it's very hard to answer without showing code and going into the intricacies of random generators, which is a very interesting topic, but one that is complicated to summarize. But usually what to do, most of the time, the data that you have to test is going to be composed of simpler bits of data. You're going to have, for example, a case class, you're going to have a record, a structure, where you have an int and a boolean and a string, and then you generate one of it and stick them into your random generator and return that instead. So very often, the vast majority of the time, what you have to do is to just compose known generators. The actual question mentioned a base 64 string that when decoded must be a legal sentence in the English language. Now that sounds very complicated because I'm guessing that in this scenario, the system you want to test is the base 64 encoder or the base 64 decoder, right? So that very specific scenario sounds very hard the way you're trying to test it, but it's actually a very simple problem to test because well, if you have a base 64 decoder, you probably have a base 64 encoder, don't you? So instead of making sure it's a valid English sentence when you decode it, I don't even know how you'd write that. How do you check whether a string is a valid English sentence? I'm not sure how I would do that. What I would do is take a random string, any string, then encode it and decode it and make sure I get the same input. And if you do that, you're more than likely faced with a working system. So sometimes when it looks really complicated to generate a random value, it might be that the property you're trying to write is not the right property. And there's a simpler property that makes it a lot easier to generate random values. I hope that answers the question. Otherwise, I have completely misunderstood what the question was about. do we have any other questions?
I think there are no more questions from. We have another question which is very, very similar, which actually regards generation of data, but of complex data actually. So we have no more questions from the audience, and because the talk is since we're here since 1 hour, I stop here.
Okay.
And we have a feedback from the person who actually posed the question, which is yes, you did answer.
Great.
So let me thank you again for being our speaker tonight. And so let's everyone thank Nicolas for his time. And let me also thank Double-Loop, which is our technical sponsor and supports us with the streaming infrastructure and so on. And let me also remind to you our Twitter handle, which is FunctionalFest, or our website, www.functionalfest.it, where you can find information about next talks, and in case if you want also you can subscribe to the newsletter or buy or book for the next talks. So thank you again, Nicolas, and thank you all. See you next time.